We are the RLC and MSD Analogy and PI Controller Group. Our presentation will depict and explain the analogy between a mass spring damper and a RLC circuit, and the building and implementation of a PI controller. We will discuss how by adding our PI controller to a mass spring damper or RLC system, the zeta and transient responses of those systems can be altered. The Ziegler-Nichols closed-loop tuning method will also be explained.
Mass spring damper and RLC systems are very similar. Both are second-order systems and their coefficients can be compared. The mass spring damper system, mx double prime plus cx prime plus kx equation, is compared to the RLC system, which is lq double prime plus rq prime plus 1 over cq. The mass coefficient from the MSD equation can be resembled in the RLC equation with the inductance. Same goes for the damping coefficients versus the resistance and the spring constant versus the 1 over capacitance. When trying to model a MSD system with an electrical components, scaling must be considered. The zeta should not change dramatically when scaling up or down.
As seen in these pictures, RLC circuits and MSD systems act in a very similar fashion. As the spring on the MSD systems is stretched, the capacitor on the RLC circuit is being charged. Both systems are storing energy to be used later. The spring is released and the mass starts to accelerate in the opposite direction to reach equilibrium. In the RLC circuit, the capacitor discharges to the inductor and the magnetic fields become greater over time. Both systems go through push and pull responses trying to reach their steady state. In these short videos, when a step is introduced to the MSD system, push and pull action is seen. This reaction can be applied to virtual physics where the cloth starts to react when the ball is being dropped. The tree also acts like an MSD system where it has a transient response when it reaches steady state.
The error amp subsystem collects the process variable from the plant and calculates the difference of that and the set point voltage. The error is then evaluated by the proportional gain in integrator subsystems. The proportional gain is the resistance ratio of the 10K turn pot over the 1K ohm resistor. This subsystem varies the amplitude of the process variable response by multiplying the error and the resistance ratio. The integrator continuously evaluates the error and calculates area under the process variable using the difference between it and the set point, all while the error is not equal to 0. In such case, the proportional gain alone is added in the summer. The summer adds the values of the PI outputs. The combined voltage is then inverted with an inverting amplifier to produce a positive corrective action value. A voltage divider is placed after the newly inverted voltage to achieve the appropriate voltage for the final control element.
Zeta is the dampening coefficient for a transient response. When we increase zeta, we decrease the transient response. When we decrease zeta, we increase the transient response. Our PI controller will manipulate zeta in such a manner so that transient response is reduced. This means that we will increase the zeta. The Ziegler-Nichols closed-loop tuning method is the method that we use to tune our PI controller. To use this method, remove the integral function from the controller. Gradually increase the controller gain until the system starts to oscillate. The set point may need to be adjusted to create a disturbance to start this oscillation. The ultimate gain is the proportional gain at the point of oscillation. The ultimate period is the cycle time at the point of oscillation. The values of the ultimate gain and the ultimate period are used with the Ziegler-Nichols equations to determine the PID controller gain, interval time.